You ever get zapped by a doorknob? Or, make a balloon stick to your hair just for fun? Or maybe you've seen the raw power of a lightning strike light up the sky? Now, they seem like totally different things, right? Well, what if I told you they're all governed by the exact same single shocking principle? Today, we're going to uncover it. Yeah, it really all boils down to this one question. I mean, on one end, you have this tiny, surprising little spark, and on the other, you have this terrifying, destructive force of nature. The answer that connects them is actually pretty simple, and it all starts with something we've all experienced: static electricity. So let's start right there with that familiar zap. That little shock you feel, it's our first clue. It's like a miniature lightning bolt, and it reveals a powerful force that's at play all around us all the time. At its heart, static electricity is just about one thing: imbalance. Imagine a scale that's been tipped way over to one side. Nature absolutely hates that. It wants to level the scale, to get back to a state of balance, or what we call equilibrium. That sudden zap you feel, that's just nature snapping everything back into place. But to really get how that imbalance happens, we need to go smaller, a lot smaller. To really understand this, we've got to see how it builds from the ground up. And I mean that literally. We're talking about the atoms that make up everything. You, me, the carpet, that sneaky doorknob, everything. Okay, so every single thing is made of these tiny things called atoms. Inside each one, you've got positive protons and neutral neutrons locked right in the center. And then you have these negative electrons just zipping around the outside. Now here's the key. In a normal happy atom, the number of positive protons and negative electrons is perfectly balanced. Their charges cancel each other out, which makes the whole atom, and whatever it's a part of, electrically neutral. But here's the twist. While those protons are stuck deep inside the atom, some of the electrons on the outer edge are, well, they're a little restless. They're not held on very tightly, and with just a little nudge, something like friction, they can be convinced to jump ship. And this explains it perfectly. So picture this. You're walking across a wool carpet in your socks. Your socks are literally rubbing electrons off of the carpet. Those electrons leap from the carpet and start to build up on your body. So now the carpet is missing electrons, which leaves it with a net positive charge. And you're carrying around a surplus of electrons, giving you a net negative charge. You've just created that imbalance. So why does this happen so well with a wool rug? Well, it's because different materials treat their electrons differently. Things like metal are what we call conductors. Their electrons can flow around like water. But materials like wool or the rubber on the bottom of your shoes are insulators. They hold on to their electrons for dear life. So when you scuff your feet, the insulator carpet gives up its electrons and they get trapped on you because you and the air are also acting as insulators. You basically become a walking, talking, charged up battery, just looking for a conductor, like a metal doorknob, to discharge on. And this right here is a fundamental rule of the universe. When you walked on that carpet, you didn't create any new charge. You just moved it around. You took it from the carpet and put it on your body. The total amount of charge is still the same. It's just separated. And it's that separation that creates a powerful tension, just waiting to be released. Okay, so let's take that simple idea of separating charge and scale it up. I mean, way, way up. Let's go from the living room carpet to a massive, churning storm cloud. Believe it or not, it's the exact same physics at play. But instead of your socks on a carpet, we're talking about tiny water droplets and ice particles rubbing against each other inside a turbulent cloud. The result, though? It's the same, a massive, massive imbalance of electric charge. So inside that chaotic cloud, all those ice and water bits are colliding, stripping electrons from each other. This creates this huge separation of charge. The top of the cloud ends up positive, while the bottom builds up an incredibly intense negative charge. That negative base then pushes away the electrons on the ground below it, leaving the surface of the Earth positively charged. The cloud and the ground have just become a gigantic natural battery, and the tension between them is absolutely immense. And when that tension finally breaks, whoa, the result is just staggering. In a split second, the air in the lightning's path is heated to a temperature that is just insane. We're talking 5 times hotter than the surface of the sun, and it unleashes a colossal amount of energy, around 10 billion watts, in a single bolt. That is nature resolving an imbalance with incredible, terrifying force. So what about thunder? Well, when you heat air that fast, it expands explosively. It creates a massive shockwave. that rapid expansion and vibration of the air, is the deep, rumbling sound we hear as thunder. So yeah, lightning and thunder, they're two parts of the exact same violent event. Okay, so nature has these huge, uncontrolled electrical discharges. But what have we humans done? We've learned how to bottle that lightning. We've figured out how to tame this exact principle to store and control electrical energy in tiny components that, honestly, power our entire world. So, meet the capacitor. And just look at that definition. It should sound really familiar by now, right? You have two conductors, the plates, and they're separated by an insulator. It's the exact same setup as the storm cloud and the ground, or you and the doorknob, just engineered on a tiny, precise scale. It's a device designed specifically to hold an imbalance of charge. Now, what's really fascinating here is how a capacitor behaves. When you start charging it, electrons rush onto one of the plates super easily, so the current flow is at its maximum. But as that plate fills up, it gets harder and harder to push more electrons on, so the flow of current slows down to a trickle. Discharging is the same thing in reverse. A huge rush of electrons flows out at first, and then that flow gets slower and slower as the plates get back to being balanced. Here's a great way to think about it. Imagine you're pushing people into a crowded room. At first, it's easy, right? But as the room fills up, the people inside start pushing back. It gets harder. It's the same with electrons. The electrons already on the plate repel the new ones trying to join. This is a fundamental force of nature we call electrostatic repulsion. It's just the basic rule that similar charges push each other away. So how do we actually measure this charging speed? Well, we use a neat concept called the time constant. You might see it written as the Greek letter tau. You don't need to get bogged down in the math, just think of it as a unit of time that tells you how fast or slow the capacitor does its thing. A really big time constant means a slow, gradual charge. A tiny one means it's super fast. And here's the really practical part, a little rule of thumb for you. Because of the way that charging and discharging curve works, it never technically reaches 100% full or 100% empty. But for all practical purposes, engineers have a simple rule. After 5 time constants have gone by, we just say the capacitor is fully charged or fully discharged. Good enough. All right, so we've journeyed from a tiny spark on your finger to a massive bolt of lightning and then all the way down into a tiny electronic component. So let's pull it all together and really see why this one idea is so incredibly important. This is the whole journey we've been on. We started at the microscopic level, a few stray electrons jumping, causing a static shock. We scaled all the way up to the macroscopic, trillions and trillions of charges separating to create lightning. And finally, we saw the technological application, learning to precisely control that charge separation in a capacitor, a component that is absolutely essential to the phone, or the tablet, or the computer you are using right this second. From the neurons firing in your own brain to the global energy grid that powers our civilization, it all comes back to this one fundamental principle. You create an imbalance of charge, and then you let nature's powerful desire for balance do all the work. That simple zap from a doorknob contains the very same physics that built our modern world. The only question left is, what will it power next?